So I can now ask myself, how might I go about actually detecting these particles? So searches for particle dark matter, how are they going to work? Because you can't use the same techniques that you use for machos. Microlensing isn't going to work here because the masses are so small and because these particles are still moving too quickly that they align very, very frequently. And so there isn't a really easy way to do this astronomically. There are suggestions, and we'll come on to those in the end. But a lot of the effort here is to do ground-based, if you like, particle detection. And so the best bet to do this is to use some deep cryogenic detector. So, you get away from your particle background. And you stick your detector in some deep mine or something like that, isolated from all the cosmic rays, everything that's going on the Earth's surface, or something like that. And then you have a sort of relatively simple principle that you work with. And that principle is that you can basically directly look for the scattering of WIMPs off your atomic nucleus. And so this is sort of a diagram, and it's not at all to scale. Most of an atom is actually empty space. Right? So you've got the electrons in shells at the edges, and then down in the middle you have your atomic nucleus. And most of that is empty space. And so when I try and, touch something, I touch the table that I'm writing on, for example, I'm not actually really touching anything here. It's not the atoms. What I'm feeling is I'm feeling the electrostatic repulsion of the electrons in my fingertips and the electrons on the table. And so you can think about contact forces as being an electrostatic repulsion. On the other hand, all atoms have these electrons at the edges, and therefore those repulsions work. If I take WIMPs that are uncharged neutral particles, you can do the same thing with neutrons actually, but you need to be well out of the way of neutrons in these detectors, and I fire them in, then what will happen occasionally is that the WIMPs will scatter straight off the atomic nucleus, whereas photons and electrons scatter from the electrons at the edge. So the WIMP scatterings are much rarer because most of these things are empty space. But in principle, you can see direct scatterings of WIMPs from atomic nuclei. And I can do that potentially in several different ways. What I do is I just put my detector out of the way and I can imagine lots of different things. So one thing, for example, I might talk about is phonons. If you don't know what a phonon is, that's fine. But then here's the principle, is your detector is a crystal. You isolate this crystal so it's very still and it's very cold, so you don't have any thermal vibration. And then the WIMP interactions rattle it, basically. They cause vibration. You measure the vibration and you detect the WIMPs. You can look at currents. So again, in my crystal, I hit my nucleus. I'm hitting it with something probably much heavier than it. And so it's actually going to recoil. So the recoil of the nucleus puts charges out of position. So I can measure the current as it goes back. If I get things cold enough, I can measure a temperature change. So in principle, for example, I hit it, it vibrates, that raises the temperature. And then finally, and quite a popular one, I can look for Cherenkov radiation. And Cherenkov radiation is caused by, it's what's called a braking radiation. It's caused by particles moving faster than the local speed of light. So obviously nothing can move faster than the speed of light and give you a signal. But if you have, an atmosphere or water, the speed of light in water is less than the speed of light in a vacuum. And therefore, when you hit your nucleus in that vacuum, not in that vacuum, in that detector, which is filled with, say, heavy water or something like that, you give it a kick. It's moving at faster than the speed of light in that material. As it slows down, it gives off a flash of light. That's called Cherenkov radiation. So here, nucleons receive a kick. Faster than the speed of light in their medium. So there's, a range of possibilities. And needless to say, given that I've described all of these possible experiments and haven't told you anything about them, there is no clear evidence for dark matter in these detectors. And that's still valuable, it's still providing you some constraint, because obviously dark matter has some total density. And so if you lower the mass of your dark matter particle, you may need more of them. If you raise the mass of your dark matter particle, you need fewer of them, and therefore your chances of interaction are less. So you're still making constraints. It's just, that unfortunately there's no detection yet. You can, of course, detect these things potentially in particle colliders. In principle, you should be able to make dark matter particles, if the energy of your collision is greater than your m dark matter particle times c squared, you can make dm particles directly. Now, you can't, of course, see these very easily. The way you tend to track what's going out of your particle detectors is you look for objects curving in your field, and that allows you to measure the mass. But if you ever saw particle collisions that didn't seem to conserve momentum or energy, then that might be because some of that momentum or energy is being carried away by dark matter particles. And then, that hasn't worked either, needless to say. And then the final idea is, in fact, an astrophysical detection. And it just comes back to this concept here that I can take two supersymmetric particles, collide them, and make gamma rays. So if I have some gamma ray spectrum of the sky, right, the gamma rays come from all over, but they're generally having a range of energy. So if I take a spectrum, and that means I take the light and I split it into its component parts, And I can express that in energy, which is equivalent to frequency, which is equivalent to 1 over the wavelength. So express that in energy versus some brightness. Then I've got some background. I have some gamma ray background from all sorts of astronomical sources that I'm not going to go into in this course. But in principle, what I could see at some point, especially if I look at some region where dark matter should be dense, for example, down in the core of a galaxy, then what I might see is a line superimposed on that, and he says as he manages to rub his line out, a line superimposed on that, like this, where E gamma is mkc squared. So what I can actually do from that, therefore, is use astrophysical gamma ray detectors to make detections of dark matter. So you can possibly detect the annihilation radiation with gamma ray detectors. Not straightforward, but possible. And needless to say, none of these things have yet worked. So we're still waiting to see what dark matter might actually be.